Okay, so I'm going to present John Cork with Marek and Tillman. You can find them in this picture. They think that they're taking a very nice, quiet nap, but actually they don't realize it, but it was extremely dangerous. So I'm going to talk again about sum of squares, but here the twist is that we are not going to use monomial basis. So first I'm going to do a small recap of what is sum of squares. So you can do it multivariate, but we are going to use univariate in this example. Suppose that you want to know whether this polynomial of degree 4 is always non-negative. If you notice that this is actually equal to this polynomial squares, it's clear that when x is real, this is going to be real, and so the square will be non-negative. Okay. Now this square, you can rewrite it as this product of matrices. And this is simply a rank 1 matrix, which is, so it is PSD and also rank 1. If you forget about the fact it's rank 1, you can basically just try to find here PSD matrix such that when you multiply this PSD matrix by this vector of monomials, you get this. And these are just linear inequalities in this in the entries of this PSD matrix, and so this is a semi-definite program. Now the issue with the monomial basis is that if you use moderate degrees, it already starts, the prime already starts being very ill-conditioned. And so in practice, you want to use order basis. So to understand what would be different with different bases, for example, if you want to do the same thing with the Chebyshev basis, you can also represent the Chebyshev monomials by the first, the 0th, first, second, third, and so on Chebyshev polynomials. So the way I like to represent Chebyshev polynomials is also with monomials. So these times when I'm going to write the monomial x squared, I mean the second Chebyshev polynomial in x. And so then when you write x squared times y, it means you take the product between the second Chebyshev in x times the first in y. And so then when you take the square of this polynomial, of these Chebyshev polynomials, so this is a polynomial that we represent with coordinates -2, 2, 2. But this polynomial is in Chebyshev basis, so this is the coordinate in Chebyshev basis. This polynomial is actually the same as the one of the previous slides, so the coefficient have changed because it's a different basis. And you can square it and you get this polynomial. So again, this polynomial will be always non-negative. The difference is that when you take products of Chebyshev polynomials, for example, the first one and the second one, you have this. And so this product is not a Chebyshev polynomial, it's actually the sum of two Chebyshev polynomials. And so in general, when you do the product of the ith and jth Chebyshev polynomials, you get the sum of these two. So if you want to take a code that's with monomial basis and generalize to Chebyshev, this makes things a bit complicated because the product of things you represent as monomial is not a monomial anymore. And also, we want also to work with many different bases. And so what we decided to do is to create this new package called StarAlgebras, which kind of abstracts the idea of basis. It even abstracts it away. It doesn't have to be basis for polynomials. So you can create an algebras for much more than monomials. For example, if you have group elements and you want to create the algebra with these group elements, you can also do it. I will have an example later. And we decided for this design with two kinds of bases. So we have explicit bases. Explicit bases are a basis that have a finite length. So you have a finite number of elements in this basis. For example, you can say I take all the Chebyshev polynomials, the 0th one, the first one, and the second one, and I want to represent some elements in this basis, and this is the same polynomials than before. So the coordinate in this basis is going to be represented by a vector. So So minus 2, 2, 2. So when you use explicit basis, the coefficients are going to be either Julia vectors or Julia sparse vectors simply. And then you have implicit basis. Implicit basis, these are potentially infinite. And so they will not be, and they can be indexed by something else. So in this case, the Chebyshev basis, the infinite Chebyshev basis, it's actually indexed by monomials. The elements are Chebyshev polynomials, but the indices are monomials. And so if you look at the coefficients now, the coefficient is something with coefficient associated to monomials. So in a sense, it's a polynomial. So the coefficients are polynomials, but because each monomials correspond to a Chebyshev polynomials, this polynomial is not the one you are representing, right? And so we created this new type sparse coefficients, which is basically, it's the same as a sparse vector, except that it doesn't have a length or a dimension. A sparse vector, it has a number of zeros element, but it also has a length. In Julia, you cannot make this infinite, so we had to have a length that's infinite, and also we wanted to be able to use indices that were not integers in a sparse vector need to be integers, so we had to create this new type. And then for things to work, what we simply did is this algebra element, we made them compatible with the mutable arithmetics. And so all the work we did for jump expressions to be able to make them to make it efficient to work with jump model, which jump affine expression and quadratic expression. The most important thing was to use the fact that this could be mutated, and so when you do operation, you should not always create the intermediate expression of the operation. It's best to create the result and then to mutate it. We use the same work to make algebra efficient with this. And so now when you multiply Chebyshev polynomials, you can use their mutability. And thanks to that, the fact that you have these rules will not make it inefficient. And then the advantage, because it's not actually specific to polynomials, you can also use it for anything. For example, if you want to create some custom algebra, here in this example, I create an algebra between 4 letters. So we have A1, A2, C1, C2. And I simply say that I have some rewriting rule. So A1 square should be the identity, A2 square should be the identity, C1 times A1 should be A1 times C1. So whenever I multiply two words, it's going to search for these and rewrite them. So there is a known algorithm known as NUT-Bendix that is implemented in this package. And so thanks to this package, you can easily create a custom algebra like that. And this is very useful, for example, when you start to work in the quantum world. You have some weird computation where suddenly the variables don't commute, but they obey some weird relations. And it's easier to define them like that. But then you're not a polynomial anymore. But because we rewrote sum of squares to not be specific to the monomial basis. At the same time, we also make it also not specific to polynomial at all. And so there is this famous SH inequality that's related to entanglement and so on, which is basically finding the lower bounds for what's the constant that you need to shift this polynomial with so that it's non-negative. It's 2 square root of 2. And if you want to find this, you can formulate it as a sum of square program with sum of squares using exactly the basis that we have defined here with this algebra, with this new StarAlgebras package. Then it's going to work. And what's the advantage of doing it with sum of squares? In sum of squares, we actually implement 2 bridges, what we call the image and kernel bridge, to formulate the equality. So to formulate basically this equality, there are 2 ways to do it. The reason is you have several entries that correspond to the same thing here, because here you have 9 entries, and here you only have 5, right? Of course, this is symmetric, so you only really have 6 entries that are not trivially the same, but still here there are only 5. The reason for this is that you have 2 entries here that actually correspond to the same thing. So this one is x times x, so it's x squared, and this one is 1 times x squared, it's also x squared. So actually you have the sum of these two that corresponds to 28. So 28 is minus 16 plus minus 16 plus 4. And so you have 2 ways to encode this as an SDP. Either you create an SDP matrix, and then you say that the sum of these 3 is equal to minus 28, so an equality. Or what you can say is you can say that you can take 16, you put it here. You take this one, you divide by 2, you put it here. You take 16, you divide by 2, you put it here. You take 16, you put it here. And then minus 28, you create a slack variable that is free. And then you put here, you put the slack. And here you put minus 14 plus the slack divided by 2, something like that. And if you do that, then you instead of creating a PSD matrix, you create a constraint that is an affine expression in a PSD that should be PSD. So a matrix depending affinely on 3 variables should be PSD, which is quite different. And typically, if you have a problem with a small number of variables and large degree, like this one, it would be better to do this formulation, because as you see, there are clashes, and if you increase the degree, there are more and more and more clashes. So it's best, if you would do the second formulation, you would just create a lot of slack variables. So it's best to create a PSD variable and equality constraints. But if you look at the case of high number of variables, low degree, like for example quadratic polynomials, it's the opposite. For quadratic polynomials, all entries here correspond uniquely to exactly 1 entry here. So if you create 1 PSD variable and then n squared equality, it's going to be much worse than just you take all these coefficients, you just put them in the matrix, and you ask this matrix to be PSD. Then you just have 1 PSD constraint, no free variables, no equality constraints. This is much better. And so it's actually very important to always check which one you should use. And this is actually not equivalent to dualization. So when you do sum of square, you actually have 4 choices. Which bridge do you want? Kernel is the first one I described, image is the second one. And also, do you dualize the solver or not? So I try to solve this problem with SCS. And then I measure the size of the resulting SDP. So this is the SCS format. I check the size of the resulting LDP. And as you can see, the best one was the kernel this time, because there are actually a lot of entries that correspond to the same one. And it's also best to dualize. So you have to dualize SCS and also ask to use the kernel. Now, as I told you, there is some kind of heuristic. If you have a large number of variables, low degree, you should use the image one. If you have a small number of variables, high degree, you should use the kernel one. So should sum of square do some kind of heuristics, check the size in the 2 cases, and then make some automatic choice, or what should we do? Actually, the good news is that usually the SDP solvers, they support either PSD affine in PSD, or they support PSD variable. And if the solver supports PSD variable and not this, you should always use the kernel. If the SDP solver supports this but not PSD variable, you should always use the image bridge. Because otherwise, just to reformulate by adding slacks and so on, it will be always worse. And you see here, if you don't dualize SCS, it's like that. Then using the kernel is very bad. If you dualize, then it's PSD variables, and using the image is always bad. So actually, if you just let the bridge use its heuristic by finding the shortest path with Bellman-Ford, it will always select the appropriate bridge. And if the user uses CS, then it will automatically select this one. And if the user decides to dualize with dualization.jl, automatically this bridge will be selected instead because it's closer to the fact that the dual support PSD variable. So then it's very simple to do. You simply define the two bridges, and then the user always has to check with and without dualization, but that's already an advice we give on the Gen docs for conic problems. Okay, then another important thing you should do in sum of squares once you start considering other bases is the sampling basis. So the idea can be understood in these two lines. What we are trying to do is encode this equality, right? So we have this polynomial, for which, for example, the coefficients are constants. We have this Q matrix that is PSD, and we should enforce this equality. So here, in the vector B, think of the vector of all the monomials, 1x squared, or Chebyshev polynomials, first zeros Chebyshev polynomials, first one, second one, and so on. And then you should make sure this equality holds for all x. Now what we know is that for two polynomials to be equal, if they are already equal on sufficiently many points, and if we know this polynomial have low degree, we already know they are equal everywhere. So for checking that two polynomials are equal, we just need to sample sufficiently many points that are different and check that they are equal for all these points. So for univariate, we already know that if you have enough points and they are different, it's fine. For multivariate, it's a bit more complicated. So a set of points for which the equality on these points means the polynomial are equal is called, they are called unisolvent in that case. But there is a way to check that a chosen set of points is unisolvent. So in practice, what you can do is sample many points and take a subset that's unisolvent. Okay, so you can do that. So what is the advantage of doing this? Because if you check the coefficients, you have a certain number of equalities. If you checked with a certain number of points, you actually have the same number of equalities because it's space of the same dimensions. So doing this is basically means that you look at the equality in the Lagrangian basis, and all the bases have the same number of elements. So it won't change the number of equalities. So why is it useful to rewrite it like this? No, this is the scalar product between one symmetric matrix and another symmetric matrix. Now, the symmetric matrix on the left has a very special property. It's rank 1. Okay? And it turns out that there are many SDP solvers that support rank 1 constraints. And even for the ones that don't support it sometimes, it's not too hard to add. So usually SDP solvers, the constraint that you take scalar product with Q, they usually represent it as a sparse matrix. And then they always take scalar product with the sparse matrix data structure, but it's very easy when you write an SDP solvers to also support it if they are rank 1, if the only thing you need to do is the scalar product with Q. And so, for instance, DSDP supports rank 1 constraints, and Hypatia also supports low rank constraints. And so I've tried a benchmark. I took random univariate polynomials that are sum of squares. I used a trigonometric basis, and then I used a sampling basis, so all my constraints were rank 1, and then I benchmarked which solver would find the sum of square decomposition the fastest. And as you can see, MOSEC, because it doesn't support rank 1 constraints, it gets quickly beaten by DSDP, which support rank 1 constraint. Then Hypatia is, I think, is more recent than DSDP and probably more optimized, so it can go in even further. And then this solver is actually specialized for univariate, and this one also takes into account that for univariate, you are always the sum of only 2 squares. So the Q matrix we are looking for is also low rank. You can search for one of rank 2. And for univariate, actually, you can show that bar searching for a rank 2, even if this becomes a non-convex problem, this non-convex problem, all the local minima are global. So you can just search over this non-convex landscape with some first order method, and you are going to find the global minimum, and so then you actually scale very easily even to that size. And also actually because I chose the trigonometric basis, there are many, like the operation to compute the gradient can actually be done with FFT, so you scale it even better. So from this benchmark, we can see that exploiting this low rank structure of the constraint matrix can be quite useful. So what I think we should do is probably add these two sets to MOI. So this set would be, so here it could be parameterized by this set. So here, to simplify, I said this is the set of PSD matrices, but it could be other sets as well. But it's mostly useful for PSD, but for example, you could also imagine using it for Hermitian PSD. And here, the set would be parameterized by a list of M matrices. And then the set would simply return the vector of scalar products of the PSD matrix with these M matrices. Now, what's the dual of this set? The dual of this set is actually this set, the set of matrices that are obtained by taking the linear combination of these constant matrices with M free variables. It turns out that these two sets are already in Hypatia. So if you look at this Hypatia set, this is exactly these pairs of dual sets. So in this set, you have an option, use dual, and if you say use dual equal false, you have this one. If you say use dual equal true, you have this one. The only constraint they have is they want A1 to be PSD. And then they have also this set, which is related to sum of squares because it's obtained when you use the sampling basis with sum of squares. But actually, this set, in this set, AI can be just any matrix that is PSD because actually you describe the matrix by its Cholesky decomposition. So the way you describe the AI matrices in this set is by giving this factor UI. So there, if it has only one columns, then Hypatia C, it's indeed rank 1. The DSDP solvers that I used in the previous benchmark support that the AI are any rank 1 matrices, and they can also be not PSD because you can use any scalar here that can also be negative. And the SDPLR solver also supports low rank constraints. And here it doesn't have to be rank 1, it can be higher rank as well. And that's the one where I already have implemented this, but there are also other examples that are listed in the GitHub issue. So yeah, it seems interesting to add them, but it's open to discussion, of course, so I'm very curious to have your opinion. And that concludes my talk. Thanks.